Okay. So, if you recall, we were discussing the Plume Rise, okay, and I gave you an expression for the Plume Rise, and we said it has two terms or two components. One was more related to momentum rise and the other one more because of the thermal buoyancy. There are many more formulas for the Plume Rise and much more accurate than one which I gave you, but for the time being we think this is all right. I mean, if you really look into the literature, you find many people have developed more rigorous formulas, and even they have validated the Plume Rise formula for the various conditions. You see here why Plume Rise is so important. If you see the expression of your Gaussian model, where does the Plume Rise appear in the formula? It is in the exponential term, and so therefore anything which is in the exponential term is very sensitive. The little change, the overall impact that you will see in the concentration could be very high. So people have essentially solved the momentum equation, the heat equations to get some formulas for the Plume Rise. But for this course, okay, we'll be happy with the formula that we wrote yesterday. Okay, and if you want more information on that, you can look for the Senfield book. Okay, that's one of the references that we gave. He deals the subject really in great detail, but for our this course, the formula which we had or which we described yesterday or in the last class is valid, and we will use that. Okay. So, if I can write that formula again, okay, let us write it again. Delta H okay. We also define the units for them, because once we write some constants, then we have to define the units. And I will again want to remind you that what were the units as far as the pressure was concerned? Millibar. Always remember that, that's for the millibar. Okay. And the other thing which I ask you again and again, this U is at what height? You can see back or at the stack tip. Okay. Don't forget that, because this is what is the wind which is influencing my delta H. How much will be the rise will be defined by the or decided by the horizontal wind at the tip of the stack. Okay. This formula for the Plume Rise is generally valid for neutral conditions. Okay. So, valid for unstable delta H times 1.2 for stable .8 to 0.9, whatever you take. Okay. So, that is the other thing you should know. Okay. I want, well, we will do something, but before we do that, I want you to recognize that, well, if I want to increase the delta H, because that is where I can minimize the impact, what are the things which are in my control? This I can't do anything about this one. I can increase perhaps the T stack, ambient temperature I have no control. Okay. The diameter of the stack I can increase perhaps. Okay. The velocity of the exit gases, that I can manipulate, put a larger blower to blow the things at the larger speed. Okay. This again I have no control onto the horizontal wind, okay. But what you see, I have no control, but this and this variation may not be so significant, but we all know the u is the one which is highly variable, okay. Sometimes wind speed can be very large, sometimes wind speed can be low and things like that. So the trick here or the thing is my delta H for given conditions, this might I can manipulate, but this I can't manipulate, okay. And then you see the delta H can, or rather delta H will be inversely proportional to the wind speed. So more is the wind speed, it means plume will not be able to rise too much, it will be forced down somehow, okay. So so there is one situation, okay, that we call as a downwash or rather aerodynamic downwash of the pollutants, okay. So that we will try to define that one, or we'll quickly do it here because it's a very simple thing. Wash of the plume. What happens is when you have a chimney or stack, okay, and this all you have noticed yourself, when wind is very high, okay, the plume instead of rising, you will see sometimes the plume just going like this. And that you must have seen from the brick kilns, for example, as you are traveling on the road, you see the brick kiln and the wind is high, then just the plume just comes on the ground, okay. Or you might have seen, suppose you have gone to the hilly areas, you know, the people do the heating in their houses and you see the plume is coming out from little chimney and it just comes underneath the house, okay. So that is what typically we call as the downwash or rather aerodynamic downwash of the plume. When it happens, when the situation is u is greater than is greater than 1.5 Vs. This horizontal wind is too high compared to the exit velocity of the exit. This is what which is going, this is u, and this velocity inside the chimney is your Vs. Okay. See, one thing will be covered by the stability, okay, in that area, whatever that stability. And in the coastal area, suppose the wind is high, okay. Now what we should do is that we should modify this one, and then this is what we take as the ratio of Vs by u. Just a second, this we should correct. Vs by u, okay, is less than, because we have to take this ratio, right? Okay. Now let's answer your question. See what you are saying, in the coastal area, what could happen to the plume rise? Okay. See, this is still, the plume rise will still be valid. Only thing is that if suppose in the coastal area wind is high, that will be taken care by the wind, and suppose the stability is different, okay, that will be taken care by these factors, okay. There are some more things which requires very special operation into the coastal area. That we will see if we have the chance to cover that thing, or if we don't have the chance to cover that thing in time. Similarly, not only the coastal area, suppose you have a large water body near your chimney. Large water body means, or within the distance of 15 kilometers, a large water body is there, and then it can influence your plume to a large extent, okay. And that dispersion modeling is little different, okay. That we have not talked about that, but maybe we will talk provided we have the time, okay. Essentially what happens is that you see at the interface of the sea and the land, or the water at the land, see the mixing height, okay, as we have seen, the mixing height is very different onto the surface of the sea or of the water, and at the land it is entirely different, okay. So that mixing height has the influence onto the land, okay. So when the wind is coming from the land, the sea side, so it has the mixing height is governed more by, because of the mixing height at the water level, okay, and that has some changes. So generally these things what we are saying is, you can say, is generally valid for the source which is almost about 10 to 15 kilometers away from a water body. Okay. But as an approximate, as a tool to take some decision, okay, this formula is still quite valid. So the coastal thing which may affect you this thing, that will affect early in the early hours, you may get little different results. But once the day has come up, then things more or less this becomes valid. But that you are right, certainly the coastal area modeling is a little different, at least in some early hours of the day. After that things become the same what you are saying. But as I again say, for routine purposes, even the coastal area, you can take this and take the broad decisions. Sometimes as an engineer you have to take the broad decisions, okay, not very minute decision whether the industry should come at the distance of 5.62 meters from the coastal area. You have to say, well, it should come somewhere from 10 to 20 meters. Yes. So then you can just look into any of the books. You can say the water air quality modeling in the coastal areas, okay, or water quality modeling at the lake shore. Okay. So air quality modeling at the lake shore, and that can, you will see the difference that will be shown. Maybe if we have the time, we will discuss that, okay, and if not, we will skip, at least as far as this course is concerned. It is slightly at the higher level, and the person who did a lot of work onto this coastal air quality modeling, or it's called lake shore modeling basically, because it is whether it is a coastal area or a large water body is there, it is the same thing. There was one person called Dr. Mishra from Ministry of Environment, Ontario, Canada. He was the very person who did a lot of work onto this one, and his work is the one which is always referred to when it comes to the air quality modeling in the coastal area or near a large water body. Okay. Okay. I want to define in the same connection for this condition. This is the correction, and D stands for downwash. This is the correction you apply to your plume rise, okay, if you are under the situation when your exit velocity, the ratio of exit velocity to horizontal wind speed at the tip of the stack is less than 1.5. It should be 1 by, correction become negative. See here, suppose your Vs by u, okay, is less than 1.5. Let us do the example since you have asked. Suppose I take diameter as the 3 meters, fine, okay, and the ratio of the exit velocity by u is less than 1.5. Let us say it is 1, okay, 1 minus 1.5, okay, that brings 6, that is equals to 3. Is that right? Right? So the plume rise which you calculated here was whatever that rise was, or minus, or if this correction is that this, or the final delta H after downwash equals to delta H that you have calculated above plus HD. Does that make sense now? So your effective plume rise will reduce because it has been subjected to aerodynamic downwash. So that is why you see that factor coming out to be negative. Alright, clear? Okay, this is the thing, and just remember, you do not apply this formula, this correction, if your horizontal wind speed, the ratio of your exit velocity to horizontal wind speed is more than 1.5. It means that horizontal plume will not have effect in bringing down the pollutants down. Okay, and this sometimes can be very important because see, you may have designed a lot of things. You might have designed a good temperature, you might have designed a good diameter. But if your exit velocity is not properly designed, you will unnecessarily cause serious problem to the people living in the area. Okay. And this, since the discussions are going on, this sometimes, one time we encountered this for a sulfuric acid plant. Okay. Sulfuric acid plant, typically the way the chemical engineers design sulfuric acid plant, they design some exit velocity of, let's say, between 3 to 4 meters per second. Okay. So if the Vs is, let's say, 3, okay, let's say, well, we are drifting, well, let's drift from what we normally want to do. For sulfuric acid plant, what we have measured, the exit velocity is anywhere from 3 to 4 meters per second. Okay. So if on some day, okay, horizontal wind speed is very high, okay, let's say it is 7, okay, okay, then what happens? Or let's say this is, we are taking a hypothetical example, let's say this is your, what number you want me to take? Suppose the horizontal wind speed also was 3 meters per second, okay, or maybe even more. You can encounter the 4 meters per second. Okay. So this comes out to be nearly something like 0.7, okay, much less than 1.5, and you will see the sulfuric acid plant, which is responsible for SO2 emission and acid mist, if you recall, that thing will be brought down, and the people surrounding in that area will suffer a lot. Okay. Because the plant was designed for such low, plant was designed as to 3-4 meter exit velocity or stack exit velocity. Okay. So these things are somehow, you see, a chemical engineer may not know all these things, but all becomes interdisciplinary when you are checking or you are doing some calculation for sulfuric acid plant. You ask him what is your exit velocity, and to give you a little feel, that exit velocity in the power plant, for example, if you go and measure in the chimney in Panki power station, this might be anywhere from 15 to 25 meters per second. So that you see the plume from the large power plants is not affected because of this action. And whereas in the brick kilns, because I gave you the example of the brick kiln, because brick kiln is most of the time what it is a natural draft. There is no fan put inside this one. Okay. If there is no fan put inside, obviously the Vs will always be determined by the temperature difference and things like that. So these smaller stacks will be forced, okay, or will face the aerodynamic downwash because of the Vs is generally very low. Okay. So you see in the village area, you go there, the brick kiln is there, and then although the temperature of the brick kiln may be something like 250 degrees, okay, but you see the plume is just washed down and surrounded in that area, and people suffer a lot. Okay, that's what the situation.
So, sir, the plume rise that depends upon the type of the source from where the emission. Suppose we are taking thermal power plant, sir. Particulate matter is high, so the density is to be high, sir. And suppose we are taking such as ready mix plants of bituminous, their emissions will be different. Oil refined, there will be different, sir. So, does that affect these plume rise?
Okay.
How are they taken?
All right. This formula, again I repeat, this is simple formula. Okay. This is based on to the density of the hot air that is going out. But these subtle things, okay, or the change in the density because of the particles, or change in density because largely it may not be the air, okay, those things are taken care by the other complicated formulas that we are not discussing in the class. And those formulas, the person who has done most of the work in the plume rise is a gentleman called Briggs, okay, Briggs, B-R-I-G-G-S, Briggs, and he is a person like must be around 85 years old, if he is still surviving, I do not know. And now he says that he gets some like 20-30 emails every day, even today, asking something about the plume rise. And then although he tries to answer, but he says most of the time, well, I am retired now, please ask to some other people who are more actively involved in this. So Briggs is a person who has done this work, and then he has accounted for all the density part, what kind of plume it is, what kind of the emissions that are there, either from the refinery or from the power plant or from the particles, the large particles, the small particles and things like that. So again, in summary, we want to stick to what we have for the time being. Okay? But the bricks, you just write on the internet as bricks Plume Rise, and then you will find the pages after pages on that one. Or you say Senfield book, look at the bricks, and then it will give you. So this point is clear, and a small thing but very important thing, because this will cause a very serious problem to the people, and the concentrations here can be very, very large in spite of all efforts that you might have made. So that's why the aerodynamic downwash of the pollutant is so important to know about that. See, we have talked about a lot about the U. In many lectures I have told again and again, take U at this tip, or take U at this, U is this, U is this, alright. Or maybe your U is, suppose your plant is, let's say, at the tip of a hill, then maybe you have to take the U at much higher height and things like that. So I have not defined you so far as to how you can find out the U at different heights. Okay, it is very simple. The formulation is like this. And this, where this has come from? Vertical profile of the wind. We all know about that. We study in pipes and open channel flow and things like that, right? So that's why this is what is your Z, and these are your. This parameter n depends on two things. Okay, stability. Okay, because that stability we can disturb your wind profile, right? And also the conditions, whether these are in urban conditions or these are in rural conditions. Okay, so wind profile. Okay, if you go to Connaught Place area of Delhi, it will become very different. The building, the roughness and things like that. And you go to the area which is like Gangetic Plain, flat terrain, things will be different. Okay, this profile, suppose there are large buildings here. This could be affected. So this n will be different for urban areas, and n will be different for the rural areas, which is like kind of flat terrain. So it also depends on surface roughness. How it depends, that we will probably not see, but what I will do is that try to give you the value of n. Okay, so the n, suppose you have a stability A, B, C, D, E, F, right? Okay. So I have given you a methodology or technique. If you know a wind speed at particular height, okay, you can translate that wind speed depending on the stability that you are talking about, and the area being urban or rural area, you can find out the new wind speed. That is what you require in your calculations. Okay. I am not giving you for the rural area, I mean, and by the way, you don't have to remember these things. No one can really remember. Okay. So, but you should have the idea that it works this how, and then you can always refer where the n is. But what you should really know is that where this has come from. Okay. The physics part you should know. Okay. Not the numbers. No one can remember the numbers, but the physics is that what we should not only know, we should understand it. We want to slightly do something more. A new thing, slightly new thing, area source. Okay. partly we had talked about the area source, if you recall, using the mass balance approach, and we did an example about, what was the example, in the city of Kanpur, the sulfur dioxide levels, etc., etc., and then whatever we came up with, the concentration should be so much. But there we did not utilize the property of turbulence. We simply assumed that everything was thoroughly mixed from the ground level to the top of mixing height, right? Okay. But then since we have developed some more theory, so we should improve our concept of the area source model and account for the turbulence and things like that. Okay. How this is done, I'll show you, but before that, what we do is, okay, what is the importance of considering the area source? See, I mean, the formula that we developed was generally for the chimney or the stack. That is what we call as a point source, because one single chimney is there, that is your point source. Okay. But for area source, it is almost impossible to go to every house, okay, and see what the chimney you have, or go to every little tiny industry and say what chimney you have. So in order to facilitate a modeling, we take that as the area source, okay, and then you see what is happening in that particular area. Suppose you go in the Bada Chora, I cannot count for every vehicle, okay, so I will take that as the area source and try to model that as the area source. So that is what is the significance of the area source, to simplify the things. Otherwise I have to do the calculation. Suppose there are 3 lakhs of vehicles are there, then I have to model 3 lakhs of vehicles. That is almost impossible for me. So this is how the concept of the area source comes in. That was the little significance that I wanted to talk to you. But let us consider the area source. Okay. Let us say this is a square. Okay. So the emission is occurring from this area. I mean, the plume is not from the chimney, but it is going like this. Okay, and this is the plan, by the way. Okay, so now how we model this one is very simple. Okay, we try to define some point source, because we can model the point source, right? So we try to find out a virtual point source. Okay, and how this is done is, I try to locate this source somewhere back, but as a little chimney. Okay. So let us say if I put the equivalent of this one at this thing and treat this as the point source. Okay. And this is what we call this as virtual source, right? So just imagine, suppose I had a chimney here and it had travelled up to here. What would be difference from having this travelled from here to here? The Q is the same, the mass is the same, but it has got spreaded, right? That is the only difference that has come. So what we do is that we say, well, all right, this was a virtual source somewhere, but right now what picture we are seeing is the source with initial spread. Okay, and if okay, this is what is a wind direction that I am assuming. Okay, this is my wind direction. Okay, you can take the other way also, the wind direction, and then you say this is the wind is blowing like this. So if you have the wind like this, you can take that as a virtual source as the wind. And but then is it real approximation? Then you are saying the chimney is located here, okay, and when at the tip of the chimney your sigma y and sigma z are nearly 0, right? Sigma y and sigma z, the spread in the plume is nearly 0. Is that correct here? This is not correct. Sigma y and sigma z in the sources already there is some sigma y and sigma z. Okay, so there is a spread already. It means it amounts or tantamounts to having say that there is some source which was a point source, by the process of the wind transportation it has already spread it to something. Okay. So, how this can be? How accurate is this one? All right. See, what you do is that when you make some assumptions, one of the things is that you do the measurements on the field. The people have done the measurements and they found, well, this is all right. And then more by the experience and empirical thing and empiricism in the modeling that we always employ. So it is based on that one. So it is reasonably accurate, because sometimes we just want to, as an engineer, you want to make an estimate, not that accuracy of the thing. Okay. So that we want to make an estimate of that one. So and the modeling is nothing but the estimates. Okay. These are not the measurements. Measurements are always much accurate. Okay. Estimates are the one which the model provides. So this has been reasonably estimate, and that's how it is modeled. Okay. You can do that. It just requires how much efforts you want to put in, right? If I have limited time, and then I would rather do this one, and even if I make this as a grid, and suppose the improvement in my predictions is not so large compared to what is the resolution I want. Okay. For large source area, large cities like Kanpur and Agra and things like that, or Delhi, you can't really do so much of tiny calculation. Of course, you have the powerful computer, you can do it, people do it, you can also do it, but this is the simple way where you can do the things quickly.
So sir, using staggered grid, sir, we can define all three components, sir.
Yes.
Yes, sir. And we can also include density, temperature, all these things, sir. So a city can be divided into regular grids of 1 1 side to 2 kilometers. In such fashion, it can be done.
It can certainly be done. And
sir, the results that it also conserves mass as well as the energy budget, sir.
Correct.
So sir, it can be a good estimate, sir. Empiricism, we can estimate.
That is correct. See, the thing is, what is your requirement, how accurate you want to be, and in order to be the accurate, you may have a fantastic mathematics, okay? You may have a fantastic grid, but if your input variables are not very accurate, okay, your wind speed is not accurate. What you are doing the measurements here, but wind speed is measured. Let's say even if I take the example of Kanpur, you are trying to do something, let's say in Sharda Nagar, and your wind data has come from the Chakeri airport. Okay, so you might have fantastic thing here, but the wind is not such a good thing, so you might still not get the reasonable results, right? So in order to get an estimate, okay, you want to apply such a thing where you can quickly see as to what is happening. Okay, but you can certainly do, you can divide it a grid of point or 500 meters or half kilometers. You can not only divide the grid in a horizontal, you can also have the grid which is function of x, y and z. You can solve the equation in every little grid, okay, and find out the concentration. You can also not only model the concentration, you can model the wind vector also. Okay, suppose you go there and you strike to a building, the physical factor has gone into your model, okay, or GIS base, then it's the wind say, okay, wind cannot go this way, then it turns this way. But that accuracy, it all boils down to how much accurate you want things to be. Okay, if you have to take a quick decision, okay, if you want to take a broad decisions, is that all right? Okay, that is why in the broader sense we do it. But if you want to do the things more accurate, more efforts are required, more energy is required, and if the situation so warrants, we should do that. Okay, and then we apply the numerical modeling and things like that. Maybe time permitting, we will have one or two lectures on the numerical modeling of air pollutants. Okay, that we will see, and there we will make the grids and things like that. And the other thing, you want to make the grid, especially when you want to have a good time resolution. Okay, I am interested in not what is happening minute to minute, I am interested what is 24-hour average. When you take the assembled or assembly of the things, your little things which you might get with your finer modeling and finer grids, they will be kind of somehow suppressed in there, and that's what is maybe your objective. If your objective is to say 1 hour change in the concentration of carbon monoxide, then you better do it this way. But I want to find out the 24-hour average sulfur dioxide concentration. I will be happy with doing this one. And in fact, when you take the larger average, many things cancel out, okay, and then you might just be happy. So it all depends on what is your requirement, what is the situation, and what you really need this one for. Okay. So, we can think that is a virtual source, okay, which is starting from here and dispersing like this, right. I can think of a point source at the upwind, and do not forget this is my wind direction. Okay. This my wind direction is like this. So, what with experience and with many other studies, we found out, suppose this distance is S, okay, sigma y0 okay, sigma y0 that you are observing here is approximately S by 4. I will confirm this S by 4 of this business in a moment. Well, exact number is 4.2. All right. So, whatever is your area of your source, okay, and one of the sides of this one is S, okay. So, you get this sigma y0, okay. For this corresponding sigma y0, this distance is what I can call this as x0 and call this as the virtual distance, okay. Now, S is known to me, that area that I have defined. Somebody has to tell me how I can find out x0. Sigma y0 is that the horizontal dispersion coefficient that we talked about, but that since I am talking at the initial, this thing I am taking initial spread is so much, okay. Please tell me how can I find out x0. We have a graphs that we talked about, that was a Turner that he developed in Tennessee Valley Authority, and what he gave was the relationship between x and sigma y's, right. If you recall, what kind of graphs we had? Normally what we have been doing so far, we know the x and we find out the sigma y, right. Okay. Here you know the sigma y0 and take the stability, let us say my stability was C, find out the distance, and this will be my virtual distance for obvious reasons, right. This will be my x0. Okay. So, you can find out the x0. No problem there. If you find the x0, okay, then it means you have physically relocated the source from here to here. Okay. Then whatever is your distance which is there, which you are of course measuring from here, okay, the distance that you will consider, suppose I want to predict the concentration at the R. So, the distance for the R, okay, that actually is, let us say xr, but for all my model calculation I will take the distance equals to x0 plus xr. Clear? For all my calculating sigma y and sigma z further down from x0. So, the distance that I will use in my rest of the formulation will be the distance or the downwind distance that I will take for my this thing will be virtual distance plus actual distance. Okay. That's what we talked as a concept. Okay. We'll do some examples, don't worry about it. But you understand what I have done. Okay. And then you can also find the sigma z similarly. I want to talk a new thing and we'll finish it. Keep some patience if we go overboard with time. Line source. Okay. Many times we encounter a situation when the vehicles are going on a highway and things like that. Okay. This is your highway or GT road or whatever you like to call, and then you have the, it's kind of infinitely long, okay, and you have the vehicles on there. And vehicles are traveling, okay. And let's say I'll assume that wind, okay, is like this, but we'll change it at some point. Okay, for simplicity, let's take this as the wind is blowing like this. Okay, so now somebody please tell me what is my x direction and y direction, because I want you to be clear as to what is my x direction and what is my y direction. This is my x direction. Okay, always the wind direction is my x direction. Okay, so as the wind change, my x direction changes, obviously. Okay. All right, then this is my y direction. Now, if you recall whatever the formula which we have developed for the point source, we'll try to modify that based on the situation we have. So, if you recall the C this, what is this concentration? At what, is it some height or at the ground level? This is at the ground level because my z equals to 0. Okay, so let's say so. X, y, 0 coming from a height of h. Okay. When you have the infinitely long source, okay, you want to define your emission rate Q in terms of mass per unit time per unit length, okay, because there you had the one point source, you could say, oh, okay. Then you want to say here what is your emission from all these things in terms of the mass per unit time per meter. Okay. So, normally you want to define in this situation, which is more acceptable to me, is that I will define this Q, which I am writing as a small q with respect to the line source, that is in terms of mass time length, if you like, or let us say microgram per second per meter. Okay. So, if I am saying that, okay, then the best thing for me is to rewrite this equation as, okay, and suppose I take a small strip here, okay, in my y direction, okay. So I can say that this amounts to the same as the large cube, okay, dimension wise. Okay, I am just considering this small strip. So under this situation, we are doing nothing great. Under this situation, I want to find out the concentration. The way I defined Q, okay, in terms of dq and the small distance in the y direction as dy. Okay. So if I want to find out the concentration, I can integrate both the sides. Okay. So C will become, let's take the constants out. Okay. Q is constant, phi, sigma y and sigma z do not depend on y, they depend on x. Good. So I can take that out. U is also not function of y. Okay. What about h and sigma z square? They also not function of y. Then rest of the thing, this is function of y obviously. Is anything else with respect to y? Nothing else. Okay. So then I can integrate this from y, which y can expand from minus infinity to plus infinity, right? Okay. Minus infinity to plus infinity. Okay. So we have exponential minus y square 2 sigma y square times dy, right? Okay. If I make substitution, okay, suppose if I say S equals to suppose I make a substitution, okay. So ds will be equal to sigma y is constant and dy. Alright, no problem there. Okay. Therefore, my dy it will be equal to root 2 times sigma y times ds. Okay? Okay. Suppose I call the whole thing as, for simplicity, this as to save some time, because we don't want to. So what you can say here, the C equals to K, a constant which is equal to this term minus infinity, limits will not change, as you can see, minus infinity to infinity e to the power exponential what else did we get? Root 2 please see it as a mistake. Okay, no mistake. Okay. So this will be equal to K, these are all constants, so that comes out exponential square negative integration from minus infinity to infinity is equal to pi, under root pi. So what I am trying to say here is e to the power minus s square Okay. So have you done the things all right? Okay, looks okay. So let's now write the value of k. K is your q phi sigma y sigma z u. Okay. Exponential. We'll write that a little later. So I can write here and then h square. Okay. So this, correct me if I make some mistake, is that what can I write here? 2q 2 pi, that is correct, sigma z u exponential minus h square by 2 sigma z square. You get something like this? Okay. Why we are writing in this form is that is how people sometimes prefer, because this is a Gaussian kind of thing, square root of root 2 pi and things like that. Otherwise you can write in the form whatever way you like to write. But many of the books, if you will see, they have not derived this thing, but they will simply give you the understanding like this. So this is your C. Make a note, Q is in what? Mass per unit time per unit length. Okay. Where has sigma y disappeared? Obviously sigma y is cancelled. Okay. What it means to you when you don't have any sigma y? It got integrated out. Wind is blowing like this, okay, and your y term is also disappeared, okay, and this is one thing what we have assumed, we have integrated from minus infinity to plus infinity, so we have taken this line to be infinitely long, right, infinitely long. So what happens in this case is that, see here, when I change the y, okay, I change the y, okay, and your emission is the same all throughout. Is your concentration any more function of y? It is not function of y. So that's why your y has completely disappeared from here. See, if I take anywhere in the y, I take the, as long as my x is the same, I measure the concentration at any place, or model measurement of course is a little tricky, but that will be the same. So that's why that got integrated out. Okay. All right. The situation is, the little variation that we need to give here is, suppose the wind direction is like this, making some angle phi with respect to the road. Okay. In that case, simply what you do, C equals to 2q root 2 pi sigma z u exponential minus h square by 2 sigma z square take the component in the x direction of that thing. So you simply do the sin phi. Obviously if the sin phi is 0, concentration will be, and cos sin phi is the phi is the sin phi is 0, then it becomes 0. Okay. What is sin phi is 90, then it is 1. Okay. But we we apply this particular thing only for phi equals to like more than like 20, 30 degrees or more. Okay. Because then otherwise you will get the concentration as 0. Okay. And so this is how we can get to work through the line source. So little variation, I could have still maintained Z here. There was no problem, right? I put Z equal to 0. If I want to maintain the Z, I can still keep the Z as intact, and Z is not function of Y, so that still I can get the expression containing the Z there. Okay. So suppose you can further simplify this one. Suppose you think your cars and scooters and trucks are emitting at effective height 0, because this is morally groundless. So you can put this equal to 0, this becomes 1. So that variation you can do. But why we are writing in terms of the H? Sometimes many of the industries, okay, we model them as a line source. One example I will give you, because that you have the background, is the aluminum plant. Okay, you have many pots, okay, and this line may run into 700 meters, 800 meters, and you know the top of the emissions are there in the aluminum smelters. So they all will be, there will be opening on the top, okay, there will be emissions. This is the plan of aluminum pot line. Okay, it's very long. Okay, if you remember, I had shown you the picture and that it looked very long. So in that thing, this may be about 30 meters high from the ground. So then you will maintain the H here. But some sources which are more or less the ground level sources, you can do this one. Okay, sometimes people set the wall of their field on fire. Okay, then you can apply these conditions. Okay, sometimes people have also tried to model the drift of the snow. Okay, like because of the wind, then there is a snow drift. Some people have applied this kind of something not exactly same, but something similar. But then you treat this line as the infinitely long, having the same emission at each point. So now you can apply this model at the situation where it wants. Time and again I say this Q is mass per unit time per meter, because many people make the mistake, and this is how you can do. So in summary, what we have done is we can model a point source, we can model an area source, we can model a line source. Okay, maybe the next class will do one example.